exercise 11.3 on the normal distribution. With the normal distribution, just like how we had the binomial or the Bernoulli sequence, it's just a subcategory of our continuous. So normal distribution is something that you would have heard of before, maybe not in that form, but there are a few key properties of it that we need to look at as well. So we're going to look at, for example, introducing the family of normal distributions, the transformations as well, which is, in my opinion, less of an important topic regarding this, but it is still something that's integral to your learning as well. We're looking at the different measures of center and spread as well with our normal distribution, and generally just how to apply this kind of question. The start of it is very complex, right? Or looks very complex, but it'll get a lot more simple as we go on. This is the normal distribution, okay? We're going to focus on a couple of key things. Number one, I'd like you to write down as a sub-note here. You might have heard of it as called a bell curve, and it's what your VCE results are scaled or based on anyway. The idea is to have your data so that the median equals to the mode, which, that shouldn't say mode again, apologies, I should say mean. I didn't even notice until one of the students looked at me like this. Median equals to mode, which equals to mean as well. So they're the same thing in this scenario. That's what a normal distribution is. In real life, datasets tend to have a bell-shaped distribution. If you have, and this will come up at the very end of this this video, if you have enough data, almost everything in life comes into a bell shape. Philosophy, I don't know. There's a lot of math principles in real life that are fascinating, but normal distribution. Most of your data is set out in the middle, right, where the y value or the height of it, of course, tells you the frequency or the percentage of people or however you want to perceive it, and the bottom tells you your value. So, for example, IQ, weight, height, etc., all comes under this, which means, for example, if you're looking at an average score of 30 in a study, in a subject, right, it's significantly harder to get from 40 to 45 than it is to get from 30 to 35, yeah? So that's how it falls under. This kind of distribution is called a normal distribution, and we'll start from the simple form of normal distribution called the standard normal form, or standard normal distribution. Can I get you to highlight or underline the following? The standard normal is given by f of x equals to 1 over square root of 2 pi times e to the power of negative half x squared. It's a lot to take in. You don't really need to know that. All you do need to know, right, is that this is the formula for when we're just working with a continuous distribution, all right? That's just our normal. Here's the function. You put in your calculator. That's what it looks like. If we put that into the calculator, which I'm not going to because it's going to take quite some time, it will just look like that. Pretty straightforward. You'll note that our function, as it goes towards the right or the left, so as it goes towards infinity, it will never reach 0. For example, if you've got a normal distribution, an actual normal distribution, and you try to get the heights of every single student in this school, right, of course, we can say it's impossible for a student to be 4.5 meters tall, right? But the possibility is technically there, therefore it can still come under a normal distribution. It will be astronomically low. It might be 0 times 0.000 all the way to like 100 zeros, right? But it will never reach 0. The mean of the standard normal distribution is 0. Mean of the standard distribution is 0, and the standard deviation is 1. The mean is 0, the standard deviation is 1. In the scenario where the question does not provide it to you and it's assumed that you know it, it's most likely going to be 0 and 1. I know it says the proof of the mean and standard deviation at the end of the booklet. I think that's not there, so you can just do your own research if you need to. It's not part of the study design. This distribution can be applied to different distributions through transformation. To adjust the mean, we translate the graph horizontally, and to change the standard deviation, we use a dilation factor. In other words, for example, if our mean is very, very large, we just move the whole graph to the right. If our standard deviation is very large, we just dilate that graph so it's very wide, right? We just apply the same ideas. This here, oops, I'd like you to highlight this section here. There we go, let's try that again. So, standard normal to a normal distribution, we use this rule here. Other way around, if we're going from a normal distribution, and I haven't included it here, I'd like you to add it in, to a standard distribution, we use this formula underneath. You will note their opposites, of course. Using this, we can find the function of any normally distributed probability density function as this. I promise this is as hard as it looks. No, sorry. This is as hard as it gets looking wise. It's not as hard as what I'm trying to say. F of x equals to 1 over the standard deviation, standard deviation times by the square root of 2 pi multiplied by e to the power negative half times x minus the mean over the standard deviation squared. And on the right is what the graph looks like. The peak of your graph will be the 1 over standard deviation square root 2x. The 2 pi, sorry. And your mean, of course, is just going to be your mean. Last formula on this page I'm going to be focusing on is this one here. This is a conversion. For example, if I want to find a certain probability of x being a certain value, this is where it comes in, right? Where x is a normally distributed random variable of mean mu and standard deviation of sigma. We're going to use this formula later on, so I'm not going to stress too much about that, but I'd like you to just focus on this component for now. To get from a standard normal to a normal distribution, we use the first formula. To get from a normal distribution to a standard, we use the second formula. Let's apply that knowledge here. Turn the page for me. Example 24. Describe the sequence of transformations which takes the graph of the probability density function of the standard normal distribution to the graph of the probability density function of the normal distribution. So in other words, from standard to normal, with the following mean and standard deviation, and sketch each distribution. I'm not going to go through each question, but I'll show you how we would do this. XY. Now, if we look at from standard to a normal, standard to normal is this first formula up here. So we're going to multiply by sigma and then add the mu and divide the y by our sigma as well. So that becomes 1x plus 3 y over 1. Or in other words, x plus 3 y. I'm assuming we're okay with describing transformations, so I won't go too in depth. But the graph itself will look something like this. And you can sketch it in your calculator if you need to, but it shouldn't be as necessary. Note that our mean is at 3, so therefore that should be the peak of our function. It should be symmetrical, by the way. And we have standard deviation of 1, which means it will go to 4, 5, 6, etc., etc. Let's do the same, very similar example here. X comma y becomes 2x minus 3 y over 2. Okay. That's less important than transformations. What's more important is the ability to apply them. That's really what VCAR is focusing on. This section here is pretty much the most famous part about normal distribution. So what I'm going to get you to do is copy down the 3 diagrams I'm drawing, or at least try your best to, because mine are going to be flawless, and then you try your best to copy down. So for all normally distributed PDF, approximately 68% of values lie within 1 standard deviation of the mean. So what that looks like is this. I should have become an art teacher. What that's saying is that plus or minus sigma, that's 68%. Now, in reality, it's not exactly 68%, but it's approximately, and that's what we're focusing on. The next diagram, we're going to do the same thing, or at least try to draw the same thing. We're going to still draw our mu. We're going to go a little bit further out and go plus or minus 2 sigma. And that area from there to there is going to be 95%. You can see where I'm going with this. The last one. We're going to go to the almost, to when it looks like it's almost 0, but not actually. We're going to go mu plus 3 sigma and mu minus 3 sigma. Am I going too slowly? Okay. And that area is 99.7%. You notice I got more and more lazy with the highlighters, but that's fine. Now this is 3 separate diagrams. In reality, it's pretty much just the one diagram. I've just separated out into 3 to make it easier to refer to, because we're going to refer to those diagrams later on when we try to solve these questions below. But the principle itself is pretty straightforward. In fact, I think it's just like basic geometry. Year 7 could do it, so I have faith. Let's look at a question. Experience has shown that the scores obtained on a commonly used IQ test can be assumed to be normally distributed with a mean of 100 and a standard deviation of 15. Approximately what percentage of the distribution has an IQ of higher than 115? Well, really, 115 I know is equals to my mu plus sigma. That's my standard deviation plus, sorry, my mean plus 1 standard deviation. So in other words, they're looking for what percentage has higher where x is greater than mu plus sigma. So let's look at this. It's saying higher than 115. So really what I'm looking for is this section right here. Higher than 1. Of course, that doesn't actually close off. We'll just do this. We're saying higher than mu plus sigma. So mu plus sigma, that's this section here. So how do I find that? Well, I know the whole thing's 100%. That makes sense. Obviously, the whole thing is 100%. So 100% minus 68% divided by 2. That makes sense. That gives me 16%. Now, you might be thinking, well, I can do it another way. I can go 50% minus half of 68%. So 50% minus 34%, yeah, that gives you the same thing. That's it. Questions? Okay. Lower than 130, so 130 I know is equal to mu plus 2 sigma. So on my graph, and I'll refer to the second one in this time because it's 2 sigma. We're looking for lower than 130, so that's this section here, all of this. So how do I do that? Well, again, you can apply many different ways. The way I'm going to do it is I'm going to say, well, I've got 95%, and I also want to find this section here. I also want to find that section on the left there as well. Yeah? So that becomes 100%, not 100%, sorry, 95%, plus that tiny gap, it's 100% minus 95% over 2. Which gives us an answer of 97.5%. Any questions? Okay, between 70 and 145, so that's going to be our, there we go, it's going to be 70, which is our, Jesus, equals to our mu minus 2 sigma, our 145, which equals to mu plus 3 sigma, and all of a sudden now we have a graph that is not symmetrical, right? Obviously one of them has 2 and one of them has 3, so I can go ahead and, well, I'm going to just go ahead and draw my graph. I know it looks like this. I know that's the 50% line. I know I'm looking for 3 sigma here. I know it's meant to be mu plus 3 sigma, so I just double check and write that there. This is only meant to be mu minus 2 sigma, so it's asymmetrical. I know that this half here is half of the 68%, so that one here is 30. So not 68%, half of 95%. So that's 95 over 2%. Any questions about that one? I know the right-hand side is going to be half of the 99.7% over 2. Yeah? If I add them up, of course, that adds into 97.35%. The thing with normal distributions is that they're almost always approximate. So really what I should be writing is approximately. Any questions? Okay, let's move on. Example 26. We're going to refer to a formula that I had before, right? But I'm just going to write it in a much more simple form. You might want to copy it down as well. Z, our standardized score, equals to the x minus mu over standard deviation. It's a more complicated form. That's a more simplified form than what we had before. So, the heights of women are normally distributed with a mean of 160 and a standard deviation of 8. What is the standardized value for the height? The standardized height value for the height of a woman who is 160 centimeters tall. We're just replacing the value. So, 160 centimeters, I don't actually need to do anything here. Well, the standardized value is just 0. Right? Because that is the mean. There is no standardized value after that. As in, there's no need to have a positive or negative standard deviation. It's just 0. Let's try 150 centimeters. What a lot of students will say well, a standard deviation is 8. So 8 less than 160 should be 152. It should be less than 1, as in negative 1 standard deviation. So Z equals to 150 minus 160. Don't be afraid about the fact that it's a negative value. Over 8 equals to negative 10 over 8, or simplifies to negative 1.2. And that sounds about right to me. Right? It's not going to be negative 2 standard deviation, because that would give me minus 16, so 144, right? It's not that far, but it's definitely less than negative 1, so I'm good with that. Last one, just as a demonstration, 172 minus 160, because 172 centimeters tall, over 160, divided by my standard deviation equals to 12 over 8, or 1.5. Questions? Okay, let's move on. Can I make sure you've got your calculator with you for this one? Alright, with your class pad, we can calculate a normal distribution just like we can with our discrete distributions as well. Suppose that Z is a standard normal random variable, find etc. To find this one, what we're really looking for is norm CDF, right? Norm, of course, being our normal distribution, C being cumulative, because in this particular case, it's negative 1 to 2.5, so cumulative. So in my calculator, I'm going to go to my main. I'm just going to clear this to make it less confusing. I'm going to go interactive. I'm going to distribution, continuous. It is a subcategory to continuous, so continuous, and then norm CDF. It'll give you your same screen, or very similar screen, as what you see in your binomial. Lower, of course, lower is going to be negative 1 in this case, and our upper is going to be 2.5. Now, in this particular question, like I said earlier, it doesn't say what about our mean or standard deviation, so we're going to assume 0 and 1. So we'll leave that blank. If you get something stupid, right, an answer that's completely stupid, double check, because I often make this mistake where I always think it's mean and then standard deviation, so I switch those numbers around. Yeah, so just make sure you standard deviation, then mean. Hit OK. And again, an answer of 0.835. I'm just going to round it to approximately 0.84. Now, to write this in an exam situation, because we're going to avoid writing CAS syntax on our exam, so it's going to look like this. X tilde n. And actually, I'll write the generic form in the top right here. It's x tilde n mu sigma squared. So in our case, x tilde n mu is 0, tilde squared is 1 squared. For the next one here, it's z is greater than 1. Similar idea, interactive distribution, continuous norm CDF. Lower is going to be from 1, because it's greater than 1. Upper is going to be, and you're going to whip out your calculator. Hopefully your keyboard's a little bit bigger than mine. You're going to switch to math 3 and use the infinity sign on the right hand side, which will give you approximately 0.16 x n 0 1 squared. Anyone having trouble with the calculator? Okay, turn the page. Turn the page. We've got 3 pages left. How are we going? Do we need a break? We're good? Okay. We can also determine the percentile of the normal distribution. Now this one's a little bit interesting. This is called inverse, right? It's called the inverse normal cumulative distribution function, right? You don't need to know the name. It's right here. Okay, so suppose x is a normally distributed with a mean of 100 and a standard deviation of 6. Basically, it's going to look like this. Each one of these lines representing 6 units across and representing a standard deviation. Find k such that the probability from x being less than k is 0.95. In other words, I'm saying, well, let's put this line, and I'm going to randomly pick a point, let's say here. Call that k, and we're going to try and find the area of this section here. And let that equal to 0.95, or 95%. Sorry, I'm going to go to the calculator again. I'm going to type do distribution. We're going to go inverse now. So inverse, normal CDF. It's really the only inverse you use, by the way. Now, the tail setting I'm going to leave for now because I'll explain it in a moment, right? But we're looking for the probability of 0.95. We've been given a standard deviation of 6, and a mean of 100. Hit OK, and it gives us an answer, 109.87. Okay, is approximately 109.87. Now, the tail tells us which end are we focusing on. Now, in this case, it makes sense. I've got a value of k, and I want the probability on the left to be 0.95. If I do the probability on the right-hand side, I can do the same thing. I can essentially just copy and paste this, replace this with an r for right-hand side, and change that to 0.05, and it will give us the same answer. The left and right tells you which side you're trying to find that probability to be. Any questions? Okay. Suppose x is a normally distributed... Yes? Oh, is it good now? Okay. Suppose x is normally distributed with a mean of 100, standard deviation of 6. Find any value of c1 and c2 such that the probability of etc. is 0.95. There are, of course, a multitude of answers. The easiest way for me to do this one is to just use our understanding of the 95%, right? So I can graph this. Again, I feel, just like with our Venn diagrams, it's a little bit easier if I just graph this. I know that this needs to be, what is it, 95%. This section in the middle. Well, by that logic, of course, this one's going to be 2.5%. And this one's also going to be 2.5%. Plenty of ways to do this question. I'm going to find what the value of C1 would be if I want the left-hand side to be 2.5. If I do the same thing and find the right-hand side to be 97.5%, that's fine as well. So I'm going to go to my calculator, I'm going to go interactive distribution, inverse normal CDF, put in the left as 0.025, just be careful you don't put in 0.25 instead. Your standard deviation is 6 and your average is 100, which gives you an answer of approximately 88.25. So I'm going to check that. Does that look about right? It does, so 88.25. Question?
Could you do like because in between two standard deviations, the area is the percentage is 95%. You just do two standard deviations away from the mean to be like, okay, that's 88 and that's 112.
Mm-hmm. Theoretically, yes. Right? Theoretically, yes. However, the problem is that it always comes back to approximation with a normal distribution, which is why it's 88.25. Right? This is more accurate. Yeah. But theoretically, yes. Let's try the other way, right? So if we want to go the other way and find C2, again, we can find the left defined as 97.5%, or we can do the right as 2.5%. Let's go with the right-hand side. So I'm going to copy and paste this, right? I'm going to change this to the right-hand side being 0.025, and I end up with an answer of 111.76. So approximately 111.76. Just to be clear, though, your answer should give a valid answer. You're saying, Alex, you're saying that from 88 to 112, that should be valid, given that it says find any value of C1, C2.
So it'd still be right.
Correct. I'm just demonstrating using the inverse. Yeah.
Will we ever have a question that asks us for exact values instead of approximations?
No. No. Good question, but typically speaking, I've not in my memory have I come across a question with exact values. Let's move on to the second last page. Applications.